All right, so I'm going to talk about the DSEC competition that that was hosted by this workshop organized by Davide Scaramuzza and myself. And just to quickly summarize again, the DSEC dataset, we have released it recently in RAL. And it's a dataset with 1 hour of driving data and about 50 sequences, day and night HDR scenes in different environments in Switzerland. And what we've provided so far is disparity/depth ground truth from LiDAR. And in this context, I also want to quickly give you a short outlook of what is new. So we added exact exposure time data per frame of the global shutter cameras. If you want to use that, for example, for deblurring, feel free to do so. Upcoming is a permanent disparity evaluation benchmark, and work in progress is also optical flow ground truth. And planned for the future, yet a bit unknown, is drift-free post ground truth. That is also asked a lot by others. Okay, so now back to the competition. So the competition task so far was this disparity estimation using events or frames on the rectified left event camera. You can see here, as an example, we have 4 cameras, as you may know, 2 event cameras in the stereo setup of 50 centimeters baseline and global shutter RGB cameras. And you're supposed to predict/estimate disparity. You're free to use either sensor combined. And I'm happy to show that we got 7 submissions, 5 outperforming the baseline that I've trained on the dataset, and 2 of them are using stereo frames as well, and all of them, as far as I can tell, are using ANN-based methods. And I'm happy that there are 7 submissions because it was a bit relatively short time. But you can see, for example, that that we have still very good performance. And so, what is the baseline performance that we're talking about? So, DSEC baseline is a stereo matching approach using only events, using voxel grids where we integrate 50 milliseconds of event data. And we use a network that was developed by Stepan Tuliakov, who's actually also listening today. It's actually practical deep stereo, but instead what we use is voxel grids. And that we evaluated on the test set of the DSEC dataset. And so, in fact, all of this baseline of these methods have never seen test data, so there is no way that somebody could cheat in this contest. Okay, so now to the winner. So, hard to tell the name, like Mohammad Mustafawi and Yengwoo Nam from KAIST and GIST in South Korea won the competition using events and frames and have 67% MAE. So MAE is the mean average error of the disparity. So this is disparity error, and they achieved 67% of that compared to the baseline, which is very good. And then the runner-up using only events is Hyakin Kweon. Sorry for the name, I cannot pronounce it. Also from KAIST, using only events, achieving 88.5% of the disparity error. So we're going to have 2 presentations now, 5 minutes each from the runner-up, which is called CES-NET, from Hyakin Kweon, and from the winner, EI Stereo by Mohammad Mustafawi and Yengwoo Nam. So if the runner-up is present, please go on and present for approximately 5 minutes, and then in the end we can have questions.
Hi, can you hear me?
Yes.
Okay, let me just share my screen. Hi, my name is Jae-Suk Jung. I also go by Jason, and today I'll be presenting our work instead of Hyuk-Jun Kwon on spatio-temporal event feature extractor for event-based stereo, which has shown the best performance for event only for only using events in this competition. Okay, so first off, we'd like to thank Mathias. Sorry if I'm not pronouncing your name correctly. For creating this data set which has the stereo RGB event data set for driving scenes with ground truth disparity. It's also well all the data is well temporally synchronized through the use of timestamps, and an event rectification map is also provided. So in this work, our goal was to demonstrate dense disparity math from only using event data. Although the data set does provide RGB, stereo RGB image pairs, what we wanted to see is how far can we get with just using stereo event data. So to approach this problem, we split the stereo matching problem into 3 different sections: feature extraction, correspondence search, and disparity regression. And so first, I'd like to note that raw event stream has a completely different modality from that of conventional frame-based images. And what we wanted to do for that reason is that we primarily wanted to focus on the feature extraction portion, which kind of helps with making up for the different modality. And in regards to correspondence search and disparity regression, we utilize the power of existing stereo matching models that are used in conventional images. So first, we'd like to mention a few event embedding methods, which I'm sure a lot of people in this workshop already know about. So first, we have the voxel, and this event embedding method is kind of part of the whole feature extraction portion. So first, we have the voxel grid representation, where we take the events and stack them temporally into voxel grids. So they would have a 3D shape of width, height, and time. And we can directly input this 3D tensor into conventional stereo matching networks. Next, we also have a queue-based embedding method, where we have a first in, first out queue, and we train a kernel network to convert this queue into event descriptors. So in our proposed work, what we did was we wanted to have an event feature extractor that can take into account of spatial and temporal information. So we decided to use a convolutional LSTM-based LSTM network. So we do believe that there's already various works that use convolutional LSTM to process events. However, we wanted to explore how we could use event voxels in conjunction with convolution LSTM to perform stereo matching. So what we do is we take the event voxel, and then we take each voxel layer and then sequentially put each layer into the convolutional LSTM network. And each of these outputs are then fused together and put into the spatio-temporal event. They are fused together to make the spatio-temporal event feature. And what we do is we take this feature and then put it into conventional stereo matching networks, such as PSMNet. So for our experiment, what we did was we split the training data sets into our own train and validation data set, since we don't have GT disparity for the test set, as Mathias said. So we had 36 scenes for training and 5 scenes for validation. We also made sure that the validation set includes 2 scenes captured in low lighting settings to kind of give some variance to the validation set. Next, for the stereo matching model, what we do is we tested 2 networks that perform well on KITTI dataset, the PSM network and the AA network. But one thing we found out was that the PSM net definitely trains relatively faster than AA net, but still pertains. But both of the networks have very similar performance. So in our experiment, we ended up just using PSM net. And we also keep the hyperparameters consistent as in the original papers. Lastly, we test the various event embedding methods that that I've mentioned earlier. So we have the voxel grid representation, queue-based embedding, as well as our proposed spatio-temporal event feature extractor. So here we compare the performance of the different event embedding methods. First, as I mentioned earlier, even when we use the voxel grid representation for the input for both AANet as well as PSMNet, we saw that the mean absolute error was relatively similar. That's why we decided to just stick with PSMNet, because it trains much faster. It trains relatively faster. And so what we did with PSMNet was we tested out the various event embedding methods. So these were the results we got on our own validation set. So in our experiment, the convolutional, our proposed method performed better than the others. And then this is the network that we use to submit the test results. And here's some qualitative results on the validation set. And we were able to also generate this error map because we were provided with the ground truth for this validation set, as it was kind of part of the training set originally. So here's a comparison with the baseline network. So baseline output. So here on top we have a scene from the daytime setting where it's driving, or it's a very nice scenery. So what we wanted, so although the baseline differs by around only incrementally, we can see that some parts like the fence are a little bit more refined. Also in the nighttime scene, things such as the poles are also much are more refined. So here I'd like to discuss some of the limitations that we found while working on this. So we only work with events, we definitely notice that events are very sparse in their data format. So that in itself is a limitation, we consider it a limitation. And events are definitely not as rich compared to RGB images. So to emphasize on this point, I wanted to address the photo to the right. So this disparity, this depth prediction result is actually from the night scene image here. But as you can see, the top side, you can see that it should most likely predict sky, which has supposedly infinite depth. But what we see here is that the network itself says that this is very close. So what we believe is that because events don't have as rich of information compared to RGB images, it actually mistakes the light post as tree. That's why it kind of connects the depth from the pole and kind of sees it as a tree. And lastly,
Jason,
we want to, yes.
Jason, can you wrap up? We need to
yeah, sure. So lastly, we want to mention that event-only stereo methods are too sensitive to embedding methods, and for possible future works, it'd be good to see some works that have event-adapted stereo matching, cost matching part, as well as disparity regression method. And as some methods suggested in this competition, it's definitely beneficial to use RGB frames alongside events. And thank you.
Thanks, Jason. Muhammad Mustafawi, are you also here?
Hello, yes, I'm here.
Okay. Remember, 5 minutes, we don't have more time.
Sure. So please, Jason, can you stop screen sharing so I could start? Okay, I hope you see my screen. Hello, everybody. I'm Mohammad Mustafavi, and this challenge which we competed in was a work with Young Nam and my professors, Professor Yoon and Professor Choi from GIST and KAIST. I'd like to thank the CVPR workshop organizers and also the DSEC challenge as well. The name of the method is EI stereo, which we used both events and intensity to predict better depth estimations. Unfortunately, parts of this work is still unpublished, so I will moderately give some details. So please consider that in advance. So as you know, this DSEC and the MVSEC is quite different, specifically what they're focusing on, which is the driving scenes, the scale of the data, which is much larger from the DSEC, and the settings they have, which is different, which the grid line of the image and intensity images are different, and they also have different baselines, and they capture much diverse scenes, let's say, in comparison to the MVSEC. And the baseline usually is actually learning an event sequence embedding. That's what they propose most. And their backbone is their previous work from the NeurIPS 18. So in the challenge, what we used is both the events and images. So as the calibration data was available, we warped the images to the event locations, and they nicely followed each other to some extent. And although the image sizes were different, so some part of it might have this loss of the warp, but still good shape. So we used the event representation that we used was the stacking of SPT that was presented in CVPR 19. We presented in CVPR 19. And the problem with the SPT or SPN is that it's dependent on the number of events that we put there. So if you use a lot of events, it will overlap. If we use less events, it might not really follow the APS. So in this setting that we used for the challenge, we used stacking based on time, which we used 0.5 seconds of the event stream and divided it into 3 sections, which each section was taken as an input to our sequential design. So this is the, let's say, general overview of the design, in which we used the events, as I said, divided it into 3 stacks and gave it to our recurrent residual design, which takes events and images together and fuses them as a tensor that could be later on used to estimate the depth with that input tensor. So we also had, we got the first place using events and intensity image, but we also used events only with our approach, and we got the 4th place as well. So by only using events with the similar backbone of the depth estimation. We already know the metrics for the challenge. We got better on all metrics, 1 pixel error, 2 pixel RMSE, and the main one, mean absolute error. And I just want to tell you that these 2 methods used events plus images, and CES just performed on events. I'll jump to the qualitative results here. So as you could see over here, this is the baseline, and this is our method which only used events, and this is the one that used the combinations of events and intensity images, and it has sharper details and, let's say, more details on different locations in comparison to the other ones. And so problems of events is sometimes if we have a lot of events going on, for example, if a car is driving by, it will consume a lot of the events and the details of that car, specifically for capturing using time, or even if we're capturing based on the number of events. This part will consume much of the events. So some other parts might not be rich as much. So that's why maybe the baseline cannot really capture all of it, although our event only does capture to some extent, but some parts are still require, let's say, the intensity images to be more rich in details.
Mohammad, consider
Yes.
wrapping up. You're running out of time.
Sure. So these are just some other samples I just wanted to show that the events by themselves cannot really perform nicely as if we have the intensity image as well, we could have much more details on different locations. Yeah, so these are the results. I'll just skip. And the take-home message is that image-only depth is good if we don't have motion blur or repetitive patterns, if we have actually enough details. And event-only is good, but sometimes it misses the details when there's no relative movements or when we have too much movement, which makes an overflow in the stacks. We saw this because we see the different event representations to get this conclusion. So event intensity depth is more than good, as it could use both events and images, the good parts of both of them, to create better depth values, but it's still challenging and open, and I believe many new methods will come and tackle this problem. So thank you once again. And yeah, that's the end of the presentation.
Thank you very much, Mohammad. And thanks everyone participating in this challenge. And I hope to see more submissions in the future when we set up a permanent evaluation. And also everyone in the workshop, feel free to give some feedback to our dataset or suggestions, what you would like to have. Thank you very much.
Guillermo, are you connected? Okay.
Yeah, I mean, we could have like a 5-minute question and then we could move on to the awards. I will make it shorter. So are there any questions for the winners of the competition? I guess I have a question, is how sensitive is the result with respect to the input representation, how you convert the events into a grid that then you pass to the neural network? I guess you have tried different ways to convert the events into tensors.
So with the amount of time we had, we were only able to test the three cases: the voxel representation, the Q embedding method, as well as our convolutional LSTM-based method. What we saw was that the event Q method is the Q stacking, its Q generation itself is a very long, time-consuming process, yet it doesn't generate as much performance as the voxel methods. And just simply using voxels is not enough to extract enough features from them. So that's kind of how we got the idea to add on the extra convolution feature extraction portion to this voxel grid representation.
So I'd like to add, in addition to Jason's talk, that it really also depends on if you're using the different stacking methods based on the time that we had or based on the number of events. So it is relatively sensitive if you use the fixed amount of the events and train on the network, but it generalized better when we try to use the time slots instead.
Then there was a question in the chat from Federico. That's kind of what we are talking about. What is the difference between yours and the 3 consecutive voxel grids? The representation, the input representation. But I think that's more or less settled. There is another one from Stepan. Did you try different ways to apply convolutional LSTM? Why did you decide to fuse outputs of the LSTM at different timestamps?
So to answer a question on that, we did actually try we weren't able to try many methods, but the one thing we tried was how we actually convert, kind of stacked up the fuse the different outputs. What we noticed is that instead of fuse giving each of the outputs of the convolutional LSTM the same weight, the last one actually, just simply using the last one did show good performance in terms, and the reason we wanted to fuse, or the initial reason we wanted to fuse the outputs of the LSTM at different timestamps was to kind of give additional temporal information to the network to better predict the depth.
Okay, there are two more questions. I think we could take one of them, for example. For event data for Mohammed, how long is the time span that you stack for every input? Is it the same as the corresponding intensity image?
So what we take as input is the input intensity image and 0.5 seconds before that. And we divide that 0.5 seconds into 3 stacks, which each have 3 bins. So that will be the input and up to the time of that specific intensity image.
Okay, I think the rest of the questions, we could take them offline. Maybe you could answer them. And let's move on.